All right, let's jump right into a classic. We're going to tackle a really well-known problem from Irodov's Problems in General Physics. If you've studied physics, you've probably heard of this book. We're going to break down problem 1.31 step by step and really see how to approach these kinds of challenges. Ready? Let's get into it.
So here it is, the problem statement word for word. It's pretty short, but there's a lot packed in there, right? We've got a free fall, then a perfect elastic bounce, and then it turns into a projectile motion problem, all on a tilted surface. Our job is to figure out exactly how far it goes before it bounces again.
So how are we going to tackle this beast? Well, we've got a roadmap. We're going to start by just visualizing what's happening. Then we'll look at each piece of the motion one by one. And at the very end, we'll put all those pieces together to get our final answer. It's a great way to make a complicated problem feel a lot more manageable.
Okay, first things first. Before we even think about writing down equations, let's just make sure we have a clear picture in our heads of what's actually going on. Drawing a little diagram is always the best place to start. So picture this. You've got this tilted plane at some angle alpha, and a ball just drops. The key thing to notice here is that it falls a vertical distance h. It's falling straight down, not rolling or sliding down the incline just yet. It just drops and then it hits the plane.
So let's translate that word problem into the language of physics. What do we know for sure? Well, the initial velocity is 0. It just drops. The vertical height is h. The angle is alpha. And then there are two huge clues. The problem says the surface is smooth, which is code for ignore friction, thank goodness, and the collision is elastic, which has a very specific physical meaning. Our mission, should we choose to accept it, is to find L, the distance it travels along that incline to the next bounce.
Let's get to our first real calculation. Before any of the interesting bouncing stuff happens, this is just a simple freefall problem. We need to figure out just how fast that ball is going at the exact moment of impact.
You've probably seen this a million times in kinematics, right? V squared equals u squared plus 2gh. Since the ball just drops from rest, that initial velocity u is 0, which makes our lives easier. So v squared is just 2gh. That means the speed v right before it hits is the square root of 2gh. And remember, that velocity is pointing straight down. Let's tuck that result away, put it in our back pocket. We are definitely going to need it soon.
And now for what is probably the most interesting part of this whole problem, the bounce itself. Seriously, how we handle this elastic rebound is the key that unlocks the entire rest of the solution. So, what does elastically really mean here? Think of it like a perfect, super bouncy collision where no energy is lost. For a big, fixed surface like this incline, it boils down to one simple rule. The part of the velocity that's going straight into the surface, the perpendicular component, it just flips direction, like it's bouncing off a mirror. Meanwhile, the part of the velocity that's sliding along the surface, it's completely unaffected. It doesn't even know the collision happened. So that straight down velocity v we found, it's not actually that helpful to us as it is. We need to see it from the plane's point of view. And that means we got to break it down into components using a little bit of trigonometry. One part that's perpendicular to the plane and another that's parallel to it. And here's where we see that physics in action. Before impact, that vertical velocity v has a component pushing into the plane, that's our v cos alpha, and one pushing down the plane, v sine alpha. Then, bam, the rebound happens. That parallel component, the one sliding down the plane, is totally unchanged. But the perpendicular component flips right around, pointing out of the plane with the exact same speed. And just like that, our ball has bounced.
With that rebound velocity figured out, the ball is now flying through the air again, which means we have a whole new problem to solve. It's projectile motion, but with the complication that it's all happening relative to an inclined plane. So, how in the world do we deal with this? The standard projectile equations you learn in class are all for nice, flat, horizontal ground. Trying to use them here would get really messy really fast. But there's a much more elegant way to do it. The trick is to rotate our entire frame of reference. Yeah, we just tilt our heads. Instead of the usual horizontal x and vertical y, we're going to define a new x prime axis that points right down the slope, and a y prime axis that's perpendicular to it. This makes things so much simpler.
Now this table pretty much organizes our entire life for this next phase. In our new tilted system, look at the initial velocities. They're exactly the components we just figured out after the rebound. But here's the cool part. Gravity still points straight down. It doesn't care that we tilted our axes. So we have to break gravity down into components in our new system too.
A piece of gravity, g sine of alpha, is now pulling the ball down our new x-axis, and another piece, negative g cosine of alpha, is pulling it into the plane along the negative y-axis. That negative sign is absolutely crucial. To find how far it goes, we first need to know how long it's in the air. This time of flight, t, is controlled entirely by the motion perpendicular to the plane, the y' direction. The ball takes off from the plane where y' is 0, and it lands back on the plane where y' is 0 again. So we plug our initial y' velocity and our y' acceleration into the good old displacement equation. When we solve for t, look at that! The cos alpha terms just cancel each other out, leaving us with a beautifully clean result. The time of flight is just 2v by g.
Now that we have the time, we can finally find the distance we're looking for. The range L is just the distance traveled along our new x' axis during that time of flight t. We just have to plug in all the values we found, our initial x' velocity, our x' acceleration, and the time t that we just calculated.
We've done it. We've done all the hard physics. We've analyzed the fall, the bounce, and the flight. All that's left is to substitute everything into that range equation and let the algebra do its thing.
Okay, time to bring it all home. We have the two key pieces of information we've derived. We have the time of flight, t equals 2vg, and from way back in the beginning, we know that v squared equals 2gh. It's time to combine them.
Let's walk through this. First, we substitute our expression for t into the range equation. Now we just clean it up. We square that second term, and after simplifying, hey, would you look at that? The two terms are actually identical. So they just add together. We get 4v squared sine alpha over g. And now for the final substitution. We replace v squared with 2gh. The g's cancel out, and we're left with this wonderfully simple final answer.
And there it is. The distance to the second rebound, L, is just 8 times the initial drop height times the sine of the incline angle. All that physics, and it boils down to such an elegant result. That's pretty cool.
But don't just take my word for it. Let's go to the source. If we check the answers in the back of Irodov's book, problem 1.31, a perfect match. That is always a very, very satisfying feeling. Our logical process got us to the right answer.
So we solved it. Awesome. But let's just think for a second. Our entire solution depended on two little words, elastic and smooth. What if the rebound wasn't perfect? What if some energy was lost, like a kind of dead bounce? Or what if there was friction on the plane? How would that change everything? Thinking about questions like that is how you go from just solving problems to really truly understanding the physics. Something to chew on. Thanks for joining me on this one.